uh, we are discussing about the parametric estimation methods of the probability distributions and which we can use for Bayesian inferencing. And there, a probability density function uh, is no, determined by a set of parameters. So the computation of probabilities uh, is equivalent to the estimation of parameters that we discussed in the last class. And we consider an approach which is maximum likelihood estimation based approach, where we are uh, we have maximized the likelihood of data given a parameter set. And the estimation of parameter means that parameter set which maximizes the likelihood. Now, this estimation can be also uh, you know, can be also computed. This task can be also done under the Bayesian framework itself, where you take care of the posterior probability of a parameter given the data. So you see that as opposed to likelihood, here we are directly computing posterior given the data. What is the probability of a certain set of parameter values? So uh, this computation involves, of course, a bit more. Uh, uh, additional computations are there. As you can see that the posterior probability is computed in this way. We have already discussed using this Bayesian rule that we compute the product of likelihood and prior, and then we divide it by the marginal probability of the data. So there, for the maximum likelihood based approach, we have simply computed only likelihood. So this is the likelihood part that we have computed in the previous case when we discussed about the estimation of parameters. But now we are also considering the prior distribution of a parameter. And we have already seen that how prior significantly influences the decision process in Bayesian inference. So in this case also, uh, if we have a prior probability distribution in the parameter space, so that will have its own effect. And we need to consider that. Right? So this is a requirement that this prior probability needs to be computed, or it should be provided. There has to be an independent process by which you should derive this probability distribution of the parameter in the parameter space. In the trivial case, if you consider it is an uniform probability, then this computation is again the same as the likelihood-based estimation. The marginal probability computation is much more complex. As you can see that we have to compute this particular integration or summation of these factors. That means probability of joint probability of the data and its corresponding parameter value. So we have to consider all possible set of parameter values in the parameter space. If it is a discrete and finite space, then it becomes a bit straightforward computations. But no, when you have this kind of continuous space, then there are different ways by which you can do it. So, but that is a complex process. Now, if I consider the prior distribution is I think the my link got broken. Is it okay? Can you hear me now?
Yes, sir.
Is my slides visible?
Yes, sir.
Yeah,
Yes.
because I got some disturbance in the link. Yeah, fine. So if we consider there is a narrow posterior distribution, uh, then uh, we can consider a point estimate of the parameter like the maximum a posteriori probability estimate of the classes. Similarly, you can have the maximum posterior estimate or a posteriori estimate of the parameter values, map estimate of the parameter values. So this is what you can do, or you can take the expectation over the distribution. That means uh, expectation of the parameter value considering the posterior distribution given the data. I mean, posterior means, of course, given the data. That itself is the definition. So this computation also you can carry out. So this computation is like the maximum likelihood estimation based approach. And this is one reason that maximum likelihood based estimation is more popular. However, wherever if you have a means to do this computation, this is more sound, as we have already considered. So one of the things that also you should note, we have discussed earlier also that the best estimate of a random variable is its mean because it is unbiased. Also, we have seen that it is also consistent. So those discussions we did earlier also. So that is why this expected value of parameter using posterior as a distribution, you can consider that is also a mean of that distribution. Now let us take a typical example how this uh, Bayesian estimate of parameter uh, no, is can be looked into if I consider a single dimensional random variable with a Gaussian probability density function as its distribution. So you have seen that we consider a random variable x, which follows a Gaussian distribution of mean mu and its variance sigma square. And there is a theta. Here, theta is actually mu, because theta are the set of parameters, but we are considering here this theta. You should take it as the parameter mu itself, and this mu, which is the expectation of this distribution of probability density function of the random variable x, it has a prior distribution, that theta mu. So just let me point out this part, that you should consider this theta as mu. So I'm not considering variances. I'm assuming no variance estimation is different. So let us consider the estimation of mu only. And you know that this t is just a superscript. Don't consider it as a raised to the power. It's a notation we have used in previous lecture also. So it's a tth instance of observation. Okay. So rather observation at tth instance, right? Okay. So now the likelihood of data given the parameter theta, while theta means mu and sigma square, and we are, as I just explained, that in our context when you are estimating here only mu, so you should apply that context. So you can see that this is the expression of likelihood. Do you agree? If we consider our observations are all the observations are following that independent identical distribution. Do you agree? Any doubt? I hope no, there is no doubt. So let me proceed in that case. And this is the prior of the distribution of the mean mu, right? Take it as mu. Theta is mu here. Take this thing as
Sir,
mu.
hello.
Yeah, please.
Sir, what is the power of E in Px given theta?
What is the power of?
Power of that exponential. We
That is
can
minus of, there is a minus sign. Is it not clear? This is the power. Sorry, exponential. E to the power minus, this whole thing is a power. Any doubt?
no, sir.
So you see that for a single observation, it is e to the power minus xt minus mu whole square divided by 2 sigma square for a single observation, right? I mean, I'm talking about only this part. Now, this part you take it like 1 by root 2 pi into sigma, right, in the denominator. If you remember that, then you just multiply them for as many as number of observations. So I say t is that tth instance, so there should be say capital N number of observations. So here it is capital N number of, this n is different than this n, so don't get confused, please. This is the normal distributions notation, and this n is the number of samples. Okay.
Yes, sir.
So
That n in the exponential is not visible, and so that is a confusion there.
okay. I hope now it is clear, huh? Right.
Yes, sir.
Fine. So I was just I just clarified that this n is the number of samples. So now you can show that the the posterior of this mu, theta means mu here, is also normal. So I'm not going to show you the derivations. You may carry out computations. You may look at the textbooks also in some cases where the derivation is given. And for that normal distribution, the mean, that parameter, is given by, this is expectation of mu, basically the given x is given by this. That means it's a weighted mean of mu and mu naught. Mu is the expectation of the probability density function of the random variable x, and mu naught is the expectation of the probability density function of the parameter mu. So that is the prior probability. So this is how your estimation of mean gets changed by this prior probability. Fine. So that is just a kind of example, typical example that how Bayesian method of computing estimating parameter is different from the maximum likelihood estimation based approach. So now, if I summarize that, no, what should be the computation involved to when we use this kind of parametric method for classifying the objects given the training examples. So as you have seen that it involves that you are computing posteriors for all classes where the individual components of the probability density functions are estimated, are computed using the parameter estimation method. So I can represent these computations in this fashion, and then what I need to do, I need to assign the class with maximum posterior. So as we have already earlier also discussed that we may ignore the marginal probability in the denominator because no, this marginal probability computation is quite intensive unless no, you are trying to find out some kind of statistical significance or the confidence of your decision. If you are not very much concerned about that, you may ignore it. But there is always a kind of catch. So if you ignore, then there are also risks and you are losing some additional information. Now, one of the interesting thing is that this particular computation can be modeled into another framework of classification, another kind of classification computation, where we use discriminant functions. We have already discussed this Fisher's linear discriminant, where you have seen that how a linear function is providing you the corresponding values, corresponding a particular functional value. And you can use them for classification in the later part. So discriminant functions, let us try to consider this discriminant function policy. So discriminant function is pretty simple. This policy is that for every class, there would be a function of the input attribute variables, or I should say function of the input X itself. Every class, there is a function of input, and the policy is that the class which is giving you the maximum value, you assign the input to that class. So this is the discriminant function based policy, and we call it discriminant function because of that only, because it is discriminating a particular input among these classes. So there are different forms of discriminant functions. Like I'm just continuing from the previous slide. You can see that I'm using the numerator of the posterior computation of this Bayesian decision process. So this is the numerator part. And also you can use the logarithm, because you know that log is a monotonically increasing function. So since you are maximizing the GIXs over the classes, similarly in the log space also the same implications hold. So the class which gives you the maximum value of discriminant function, the same class will give you the maximum value over its logarithmic space also. But the advantage of this conversion we'll see computationally later on. One part particularly, this product terms gets additive if you use logarithm. And moreover, you can see that in a Gaussian distribution, this exponential term, it also becomes a linear term in the function. So we'll see that. So now this is exactly what I was indicating. We are going to find out that if I assume that this class likelihood of data is Gaussian following this particular distribution. So our discriminant function is given in this form. That is the posterior function. You can see that actually this discriminant function takes care of Bayesian inference rule, because this part is taking care of the prior of the classes, and this part is taking care of the likelihood of data given the classes. And we are not considering the marginal probability, because here we are simply comparing the values. And since data remains the same, so the denominator part of that particular Bayesian inference rule, that denominator part you may ignore. So this is the form of discriminant functions, and you can see how this form, I said it is linear. I'm sorry, it may not be always linear. In fact, it is not linear here. You can see that in this expression, it is basically quadratic over X. Here, I'm assuming X is a single dimensional random variable, right? So our discussion is with respect to single dimensional random variable, because this normal distribution is also called the single dimensional random variable. Any question? So this is how a discriminant function looks like under the parametric framework. And so the method remains same. You estimate this for each class you estimate the expectation or mean and standard deviations, and then you simply compute. And also you should also compute the priors of the classes, class probabilities, and then you can use this discriminant function. Now the first term can be dropped. There is some error. I think it is trying to say the prior. If the prior is the same, then that term can be dropped. That means it is not the first term, it is the last term, that is log of probability of Ci, right? So that is what it is saying. Oh no, what? Oh, sorry. It is first term means minus half log 2 twice pi. Okay, it's all right. That is minus half log twice pi. That's a constant, so you can drop it. And also, if the prior is the same, the last term can be also dropped. And then middle two terms, minus log sigma I and minus x minus mu I whole square by 2 sigma I square, that remains in the discriminant function when we are assuming priors are same, which means we are simply using likelihood in that case. And in a typical case, if you have further simplification, that the standard deviations of all the likelihood density functions, they are same for every class, then you can ignore sigma is also. So which means then this becomes simply the classification of data X to its closest mean. That means you consider the class represented by its mean, and you compute the distances from X to that mean, and it's a distance is basically, it's a single random variable. You simply take the absolute difference between these two values, and whichever is the closest, that class should be chosen. And it is also called nearest neighbor classification. Now, as I just mentioned, that discriminant function-based classification approach, it could be more general. It need not be under always Bayesian framework. Now let us extend our discussion for the multivariate cases. Like we have considered earlier univariate cases. Now let us consider your random variable is an element. I mean, it is an element of a, it takes value, rather, I should say. Random variable takes value from a d-dimensional space, real space, as you have seen in my notation. And you can represent it as a data matrix. So as you know that in a data matrix, each column represents a particular instance of that random variable. Here it is row. Here it is row. So it is not uniform. I mean, you can see that each row represents here the instance of that random variable. I hope it is clear to you in my notation. It is not column, it is row. Oh, right. It has been written here also explicitly. So each row is a data sample. And we consider the mean vector of that random variable is this, which is a d-dimensional vector. It should be mean of each row. No, sorry, mean of each column. That is correct. Mean of each column, because these are for each attribute, these are the instances. So it is mean of each column. And also you can define the covariance matrix. Can you tell me what should be the expression of this covariance matrix with this row vector representation of data matrix? Anybody? I feel most of you are sleeping. So let me then ask questions.
The x minus mu transpose into x minus mu.
Yeah, very good. Others, any doubt? So it is x minus mu transpose into x minus mu, right? I hope I have written in this way, right? It should be expectation, of course. You have to write expectation, and this is a simplification. Anyone has any doubt on this expression? This is another additional information. In fact, no, yeah, we are dealing with covariance matrix, but there is also a concept called correlation matrix, and where you can convert a covariance matrix. Again, I am having some disturbance. Okay, is it okay now? Can you see my slides?
Yes, sir.
Okay, so I'm having frequently this kind of disturbance today. So this is the correlation matrix I was just mentioning. It is just a mention. I just mentioned it here. I think I have not used it in my discussion further. So this is your multivariate normal distribution. You can see that we have represented our probability density function, and I hope here x minus mu x is a row vector representation. We need to check, but I think that is why I have taken this row distribution, row vector representations. We need to check that also. Okay. So this is very standard distribution. And this is the exponentiation, the term with exponentiation, that is also considered as a distance function, Moholy-Nevis distance function in the multi-dimensional space. So the likelihood of data is represented under the same framework. That means you consider a normal distribution in the multidimensional space. So each class will have a mean vector and a covariance matrix. And if I use the standard discriminant functional form where, as I mentioned that you use that logarithm of the likelihood plus logarithm of the prior, then you get this particular expression. It's very direct from the expression what is shown there. Is it clear? Fine. Okay. Fine. So
Yes.
so in the multidimensional space also, you can see that it's pretty simple extension of the computation what you did in a single dimensional case. Yeah, Shattoki Dash, maybe no. You can remove your mute. Somehow no, you are in my screen. Okay. So you can estimate parameters by computing mean vector and covariance matrix from the samples of each class. And this discriminant function, its form is a quadratic form. That also you can see that x minus mu transpose, and then sigma I inverse and x minus mu. So that would give you a quadratic form of discriminant function. So what should be the dimension of this particular term? Can you tell me? What is the dimension of, if I make a dimension analysis, what do you expect? What should be the dimension of this term?
Which term do you repeat once again?
Pardon?
Which term are you talking about? Would you repeat once again?
So I'm just indicating it with this color. Can you see that? X minus mu transpose epsilon I inverse X minus mu.
It's not in my screen actually.
Uh, can you see the slide?
Yes,
The,
but
the
Yes.
multivariate
the
normal
last
distribution.
yes, quadratic discriminant function is the last line that is coming.
Yeah, that is fine, but no,
Yeah,
I'm drawing.
yeah, it's there.
Maybe it is delayed. Huh? It is getting it
Yeah, now
because of network delay is there. So this is the term. Yes.
Yeah, 1 cross 1.
Yeah, it should be 1 cross 1. That's right. That means because it's a function, see, that dimensionality mismatch, matching should be there. So it's a scalar term. It's a function of the attributes of X. Okay, that you agree? And that form is a quadratic form. Is it clear now? Okay, so you can see that that form will be a quadratic form. And now that is the thing that now if the covariance matrices are the same, you know that for the single dimensional case, when the variances were the same, then it has become simple nearest neighbor classifications. And actually that is also a kind of linear discriminant functions. Similarly, here also, it will be simple function. I mean, it can be a linear function. Now, we are continuing this discussion. In a special case, if the covariance matrix is diagonal, then we can simplify these expressions in this form, right? So it looks like almost the linear combination of all independent attribute sets, the contributions towards that quadratic term of the attribute sets, and scaled by their corresponding variances. So, so this is what, and you can see that actually it becomes a nearest neighbor classification in the multidimensional space also if all the variances are same for every class. So for every class, for every attribute, if all the variances are same, then it becomes a simple linear classification. Again, I am having disturbance. Okay, welcome back. So let me consider another case. We have considered the case of a continuous random variable in a multidimensional space, and we have also assumed that the distribution is a normal distribution. Now, if I consider a discrete random variable in a multidimensional space, which means you have discrete attributes taking one of n values, and if I assume that each process is a Bernoulli, so in that case it is two values. In that case, we are assuming that the binary cases of the Bernoulli process. So the attributes they would be either 1 or 0, and the parameters for each parameters involved in that process in the multidimensional space. That means for each attribute given a class, you have its corresponding probability of that attribute becoming 1. So it's a very simple expression of simple extension of varied Bernoulli distributions with this representation. It's simple product of all the probabilities independently for all the attributes, and this is the expression. So there are d attributes, so you have d product terms. Any query? Any kind of question on this particular likelihood expression of data given a class? So once again, that log representation is convenient. So in the discriminant function, if I take the log of this likelihood, and also the log of the prior. So that is what is discriminant function. It's under the Bayesian framework. So there you can see this function gets simplified in this form. And remember that values of xj could be either 1 or 0 in this form. Sorry. So now you can see that this is also a linear, linear functional form. So it's a linear function. So let me discuss one such application. Consider a document characterization, say news items. Sorry. You represent each document by a vector of, say, bag of words. That means each word denotes a dimension there. And the presence of that word in the document is either it is present or it is absent. So that is the Bernoulli process for each attribute space. So we can compute these probabilities, class probabilities of occurrences of each word, which is represented as Pij here. And then you can obtain the discriminant functions as we discussed, as we have shown in the previous slide, and use it. That's all. Any question? You can generalize it to multinomial cases. That means when you have multiple discrete values for a particular attribute, suppose each attribute can take one of nj discrete values. So each are independent domain in that sense. Each attribute is an independent domain in the discrete dimensional spaces. So just for the jth attribute, let us consider that you have these are the representation, and you can define then a dummy variable zjk in this form. That means we convert all the attribute variable xj to if there are that nj number of discrete values. So there are how many variables jk. So here you have nj variables given the xj. So sum of nj discrete variables you will get. So Pijk is your new Bernoulli, or I should say multinomial distributions parameter. It is not Bernoulli in that sense because it is not binary values. And the extension of multinomial distributions can be simple extension. It is product of all these probabilities within that particular class. And then you consider each attribute, D attribute, so there will be again D product terms. If you also use this particular expression, then this becomes your discriminant functions. And again, it is linear over zjk. So if I just summarize the parametric methods that we have discussed so far, that you can see that we are using this approach. That means we are estimating parameters for computing the likelihood probabilities, and also posterior. We can use it also for computing posterior, and then use it for estimating the parameters. So I mean, that is, sorry, so for computing likelihood and posterior for the Bayesian inference probabilities. Also, you can convert this particular computation as the computation of discriminant functions. So under the framework of discriminant function based classification, you can also map this problem. And on the other hand, if I have a discriminant function based classification, I can provide some kind of Bayesian inference framework for that. So it also indicates that. Then the mean and standard deviation of classes in feature space from the parameters of normal distribution that we discussed. Probabilities of occurrences of Bernoulli features also, it form the parameters, and the same analysis could be extended for multivariate class distribution. So any question regarding this parametric method for for applying this Bayesian inference in classification? Okay, so if there is no question, just I will start, or I will go to the other part of this topic, that is the non-parametric approaches. And here also we could see that our objective is also to compute the posteriors. We'll see, but computation can be mapped in a much more simplified manner, can be done in a much more simplified manner, but though there is an interpretations from under the Bayesian inferencing framework. So that is why we are also saying that non-parametric method, because essentially we are considering the probability density function. We are computing the probability density function. May not be always explicitly we are computing it, but that is also taken care of under this same computational framework. And for every classes, here explicitly you are trying to compute the posterior probability of that class given the data. So explicit computation without going into the parametric based, method based, I should say, computations of the probabilities. So we are just considering the data, and we are observing, and almost similar to the method by which you have computed priors of the classes in the naive Bayesian classification rule. We have computed that kind of likelihood probabilities and prior probabilities. You will find it is pretty similar to that, but no, we have a better understanding of the process that we will also see, particularly in the continuous domain. So their naive Bayes classification we discussed with respect to discrete in a discrete for the discrete random variables. So in this case, the assumption is that the similar inputs will have similar outputs. So other term for this kind of assumption is that it's a learning using instances. So we can also call this kind of method is instance-based learning, but again, the Bayesian interpretation for that instance-based learning also we'll see. As it is non-parametric, there is no assumption on the form of density functions. So we estimate the probability density locally. So what we are doing, the probability density of the random variable, either the marginal or the likelihood, that means given the class, we are trying to compute it locally. Okay. So, and prior computation is pretty direct, because as we have seen earlier also for the naive-Bayes classification, if I assume class the particular attribute of class levels, that is discrete, so prior is pretty simple. But when we are considering the random variable in the continuous domain, then that is interesting to see that how this kind of local estimation of the density function is carried out in a non-parametric way. We have mentioned that when we have used parametric approach, that is the kind of, I should say, contrast, that in a parametric approach, we have estimated a density function using all samples together. But in this case, we will be considering local to a particular point. So if we would like to compute the density function at a point in the input space, at an instance, if I say, at a point, if I say, then whatever locally available, so we define some kind of neighborhood around that point and observe what information are available to you from the training set. Use them only for computing the probability density function. So that is meant by this local computation. I mentioned this flavor of computation. It's an instance-based or memory-based learning. Of course, you need to store samples in a memory for lookup, and that is what is the training part. But it is quite computation intensive, because you see that in the previous case, when you are classifying an instance, you are simply computing using few parameters only. Suppose there are say k classes. If there are k classes, so you are computing k discriminant functions for each instance. Each discriminant function, that I told you that interpretation comes from the Bayesian point of view also. So the order of computation, it simply for that instance, it is order should be, for a single dimension, it is k order k, but no, if you have d-dimensional space, it should be k into d kind of thing, order. Or it would be more. If a d square parameter set is also there, covariance matrix. So it is basically, order is the number of parameters and the number of classes, product of that. Whereas in this case, it is this order is, I'm saying that at least, that means no, if you have more computations, the order will be affected. But at least that is what you need to do. You need to consult at least and get access of those set of parameters for the parametric part. Similarly, for non-parametric part, you have to access all these instances for computing these local density functions. So here, the order will be of the order of number of instances, which is much larger than the number of class and number of parameters. So this is what parametric approach, order D, it is a single test of the dimension or D square, as I mentioned, number of parameters, depending on the number of parameters. And the other other characteristics is that it's a lazy learning. I can explain these things better as we proceed. So let me stop today, because we have almost run out of time.